Alrighty, I should be now live. Hello, everybody. Everybody on the Small Gaps YouTube channel. Hello. Hello, hello. Let me just say everything up. It's been a while since I posted to this channel. Since August 2025. It's been a year. Or maybe less. That's when I did the video last. The live stream was in May. It was in May. That was my last live stream. It's been a long time, man. Well, anyways, guys, today I did some digging around and I meant to find out that there is indeed another whole book about, well, making your own LLM from scratch. And so that is today what we're going to be doing, because you gotta learn every single time, let me do some coding. There we go. Because, like, getting a job is hard, man. Getting a job is hard. Gotta continuously learn and all that sort of stuff. It's just, it's really insane. But anyways, let me get all this sorted out. So today, actually, let me put the Lo-Fi Girl on as well. Hold on. Where's Lo-Fi Girl? Wait, Lo-Fi Girl's stream is not on. Where's Lo-Fi Girl? Lo-Fi Girl. The stream that I usually put on is not on right now. What's happening with Lo-Fi Girl? Did she... I need to put on Lo-Fi Girl. Hold on, guys. Hold on. Lo-Fi Girl is important.
This is your brain when you're struggling to focus.
Hold on. Let me sort out the Lo-Fi Girl stuff. Interact, skip. There we go. There's Lo-Fi Girl. Alright, so yeah, I did some stuff. So today we are gonna be doing just that. So as you guys can see here in the top of my head, there is the book that we're reading today. If you guys want to read that as well with me, the book title is Build a Large Language Model from Scratch. It is a book by, I'm gonna lose the page if I do this. Hold on. 33. Oh shoot. Page 33 by Sebastian Rashka. Now, this is basically, I think, the same person that has, like, what's it called now? Done books on a whole lot of other languages and all that sort of stuff as well. How can I tell? It's the same style of picture that they use. It's just how it is. Anyways, let's get all of this started. So I've actually done... let me get back to the page that I was on. 73, that's too far. 20. We're gonna try and do this all, not all of it, but we're gonna try and just get everything sorted out this night. Like, we're gonna try, I got my coffee with me. We're gonna try and do some midnight coding here. Bite-sized and coding. So yes, I've done some stuff. So at the moment, I'll let you guys know on what's going on. So we got this here. This is the verdict. This is a corpus. It's basically a text, right? Hold on. Like a stream. Wait, let me get the chat. Okay, there we go. Alright. So yes, this is a corpus. This is text. At the moment, what we've done is that we've just learned how to tokenize it. So tokenizing, if you guys don't know what that is, it is basically each of these words and things, they are a token. For example, Gisborne had, that Gisborne is a token, had is a token, this part here is a token. All of those stuffs are tokens, right? It's basically how it's basically when people talk about tokens in what's it called, like in ChatGPT and all that sort of stuff. That's what they mean. That's what they mean in terms of tokens. It's basically the amount of data that it has information with. So that's what I've done here. That's what we've sort of read up upon, and again I'm on page 31, and we're just adding unknown tokens as well. So this is quite important information if you're doing it from scratch, because yeah. And again, we got, I don't know, it's gonna be fun. I don't know. The hell is XMT? And now it bites parent encoding. So I'm just gonna literally just read in my mind, and then you guys can read on your own pace as well if you feel like it. So I am gonna need the Conda Navigator though. Oh man, I'm tired already. We just started. I gotta drink some coffee, but it's too hot. The coffee's too hot. But I'm in my puffer jacket and it's winter though. Man, why it be like this? It's so cold. And the Conda Navigator is fixing itself up. Okay, there we go. Let me get this sorted out. Wait, I don't need a Conda Navigator. No, I just need terminal. Terminal. No, not this one. Terminal app. There we go. And then the Conda Navigator PowerShell. There we go. Base Conda activates LayBlues LLM. We're gonna ls, we're gonna clear, and then pip install TikTok. And wait, is it in pip? Yeah, it's in pip. Oh, already got pip TikTok and then. Okay, let's put it here. So we can just copy and paste the code, which is really nice. Let's check our thing. Version 12, okay. Can initiate a byte pair encoding from the TikTok as follows. I don't know what the GPT-2 part is. Oh, gotcha. Okay. So this is basically, instead of our tokenizer that we did manually here. So instead of the tokenizer that we did manually here, it is just its own tokenizer in the form of GPT-2. I'm guessing if we did GPT-4, we could do the same. Usually via the encode method. Let me get this. Let me copy this. I want to check if there's GPT-4. Wait. What is the latest GPT version? ChatGPT 5. Okay. TikTok and get encoding. OpenAI's models. Okay, TikTok and just reading some things at the moment. Fucking face TikTok and oh, there's a lot. Interesting. Okay. Alright. There's no real information. Oh wait, GPT. No, they got GPT 4.0 and all that stuff as well. Yeah. Let's see. Byte token. There's nothing here. There's no. Must be in the code somewhere, outlining all the details of what you can use. Okay, let's go back to that code here. Let's see. So, open up in Data Wrangler, so we don't need to do that. So that turns into that. So that is exactly the same. No, it's different. So, but if we do this, we footprints. And then when you convert the ID tokens back into code using the decode method of the tokenizer from TikToken. Alright, so why didn't I don't know, dude. I was doing some Mistral stuff, so it's different as using ChatGPT's one. GPT-2's one, but this is using the normal thing. Printing the integers, printing the string. That changes it to string now. An unknown. Oh, okay, yeah. It is. It is, okay. Wait a minute. I just realized, so this is the whole vocab of GPT-2. Huh. Well, okay. Okay. Wait. Just take open the whole vocab of GPT. Let's see. Organize text. Optimize through TikTok and ensuring yes. So. Trained using O200. Okay, so interesting. All right. Well, there. See, I didn't know this was a thing until now. This is really useful. Okay, contains the info about additional tokens of. Okay. So it doesn't contain additional tokens. So if we, for example, were to put Whoa together from Cute and Funny on Blue Archive, they wouldn't know what that is. That we'd have to do that manually potentially. And again, as a new token, but I'm sure that we can do that as well. Somehow, we'll see how we can go. But otherwise, we need to make our own TikToken, our own one. Figure out how to do it. It all depends. There is Hugging Face Tokenizer JSON though. But there's two different ones. Alright. Okay. I don't know. Okay. Yes, end of text being assigned the largest token ID. Second, the BPE tokenizer could indicate unknown words such as correctly. The BPE token can handle any unknown word. How does it achieve this? Using unknown tokens. Okay, so it can actually do it. Alright. The algorithm underlying BPE breaks down the words that aren't in its predefined vocabulary into smaller sub-word units or even individual characters in the ability to handle out of vocabulary words or so things to the BPE algorithm. If the tokenizer counts on it can represent it as a sequence of some tokens as it. Or we added in, I think that was one of the things that we learned in what's it called now? I think I remember we covered this in an LP in university as well. We made our own tokenizer from scratch, included everything that was ever possible. Take example of those unknown words, tokenize into individual ones. That's right, and then we bring up a new one, and then I guess that is. So let's see, 1, 2, 3, 5, 6, 7, 8, 9, 10, and 12. 1, 2, 3, 4, 5, 6, 10, 11. So it's unknown. But it caused it to be larger though. But you know what? I think that's also how it creates the correlation between the other words. Actually, that's pretty good. Just break down into the word doesn't need to replace unknown words with special tokens such as unknown, which is really good. Because I wouldn't want to unknown. Sorry, excuse me. Alright, so now I'm gonna create the data loader. Basically, we're gonna be separating everything into the test data, validations, all that sort of stuff. All the goodies. So, gonna read this and then we're gonna encode it as well. So get that, and then the encoded text, we're gonna print the length of that as well. So the encoded text is 5,145. Yes, total number of token the trading set after applying the tokenizer. That's right. Next, we remove the first 50 token from the set for demonstration purposes, as it results in a slightly more interesting text passage in accept. Okay. So let's get the sample and just do that. So now it's talking about context size. Alright, so one of the easiest to create the input, target pairs, word prediction task to create two variables x and y, where x contains the input tokens, and y contains the target, which are inputs, shifted by 1. Okay. Alright, let's try this out. So context size 4. Gonna have context size of 4. And now we have that. Oh, that in. Oh, no, that's too much. There we go. So, yes. Get out of this works really. Let me. I'm gonna ask Google. Google, wait. Google. Google AI. Where's Google? Wait. Google Gemini. Just ask Gemini. Explain this to me. Let me sign in. Okay. Is Google Gemini free and unlimited? This one I need to know. Because ChatGPT is not unlimited, unfortunately. But it's not unlimited. They access limits. Oh no. Oh no. Okay. Oh. Explain to me how this works. Explain to me how this works. Now we're gonna go complex problem solving and pro. No, Pro is using a high demand at the moment. No, I got Flash instead. Dang, that sucks. I got the dumbed down version for a complex mathematical thingy. Anyways, let's see. This guy demonstrates fundamental trick. Shift by 1 alignment. Okay, so the next target token, the next one after that. Looking down the loop, what it means. Model sees, they must rotate. Interesting. So, through the magic of attention loss, it calculates the loss for all these predictions simultaneously in a single forward pass, rather than letting a route 4 separate times, which is very efficient. Okay. So. don't get it. Something's off. Wait. So we're encoding all the raw text. So this is the input tokens that you've typed, and Y contains the target of what the next is going to be. Or essentially when you put it into the loop thing, it goes and goes and goes, okay. Yeah, I think I'm starting to get it. It's a bit hard to explain. Again, I'll create the next word. Predictions. Okay. So I got that. Okay. Because of this, the next one's gonna be this one, this one, this one, the next one it's gonna be this. Yeah, this is okay. This is not okay. I gotta think of it this way. This is not the full LM stuff. We haven't included any convolutional neural networks or anything of that sort as well right now. Everything to the left refers the input an LM would receive. Yes, indeed. And the token ID on the right represents the next target token ID that I'm supposed to predict. Yes, that's right. There's code, but convert the tokens IDs into text. Okay, now we're doing it into text. Yes, I got the idea right in that sense. Let's put it through that and establishing. And the following, yes, that one is correct. Not creating turn tokens into embeddings. Implement an efficient data loader that iterates over the input dataset and returns the inputs as PyTorch tensors before the multi-dimensional arrays. In particular, we're interested in returning two tensors: an input tensor containing the LMCs and a target tensor. Ah, okay. Alright. The AI can be so confusing. I feel like I'm learning what quantum physics again. The quantum computing again with U#. In a string, for manipulating the code, manual operate and token IDs directly since the yes. Yes, okay. So alright, so we're gonna turn those into tensors. Gotcha. Tensor containing the inputs, containing the targets, yes. Efficient data loader implementation, we'll use PyTorch once. Okay. Oh my gosh, I really hope that this works with the Radeon. Okay. Okay, I'm gonna need to copy this from the chapter thing here. There's another different thingy-majiggy. Where is it? This one here. Okay. Let's copy this one. There we go. There we go. Copy that. Paste it in. It's based on title show. The client defines how. Alright, let's look at this first. The GPT dataset v1 token enters, we tokenize it. Assert that length of tokens, number of tokens input must be equal. Using a sliding window to overlapping sequence for max length. But input is that plus the max length plus, and then this one is plus the max length plus 1, and then we append the inputs. The self input ID is the append. Okay, yeah. All right. Okay, so basically tokenize the whole thing inside the text and then put it straight in this. And okay, all right. Each row consists of the number of token IDs, base consists of the number of token IDs based on the maximum emphasized. Hold on, get my head around this one. So defines how individual rows are fetched from the data set. So let's see. By each row of the things in the text file consists of a number of the token IDs, yes, based on the max length of the vocab, which is the tokenizer, yes, assigned to input chunk tensor, yes. Target chunk tensor contains the corresponding target, yes. I recommend that. And from this, it looks like when you combine the data with PyTorch to the letter, it will bring additional intuition and clarity. Yes, it probably will. We can access that in a bit. Such as shown in listing, refer to 8.6 and to explain general structure and usage of data set and data loader classes. 1. The following code uses. Actually, where is that appendix? How do I access an appendix? How do I do that? Fortunately, I don't know how to do that. Where is the thing here? How can I view all tools? That's not it. Edit convert? No. That's not. How do I? How do I view the pages? How do I do that? I view the upcoming pages or list of pages. All tools, maybe. No, that's just a thing. Most pages? No, it's all. No, not that one. Okay. Time to just go and open with Firefox. Not Firefox. Open with Slurp. Alright, let's see. There we go. Now I can view it. Alright. Appendix. Oh, appendix. Here we go. Appendix A and 6. Okay. Got all the details there now. Just read this through. Ah, okay. So this is what I learned in university. So setting up efficient data loaders. Sorry about how to do this manually. It was a pain. You know, I'm just reading this now. Did you guys know that the data loader actually has a shuffle feature? I didn't know it had a shuffle feature. Dude, you know what, guys? I'm giving this to Gemini, and it is explaining batch sizes a whole lot easier to me now. I don't know, I need a refresher once in a while. I know what batch sizes are, but it gets lost on me, man. There's so many AI stuff every time. It gets lost. Like the error, the loss functions and all that sort of stuff. Which was a pain to deal with. Okay, April 10 batches have passed with model 1 epoch is complete. Okay. Hardware limits. If you try to load 50,000 high resolution, you'll instantly Batch with no footprint magical grading. So if the batch size is 1, trading is chaotic and bouncy because the model reacts wildly to every single individual error. So that's why we want to average it out, I guess. If your batch size inside data says it updates are perfectly smooth, but it takes a massive amount of time just to make one tiny adjustment to the weight. Okay, so that's also interesting information. Mini batching, commonly sizes like 32, 64, 128, sweet spot. I'll see if I can do that. Enough to learn effectively, but noisy enough to help the model escape some suboptimal traps solutions. Okay. Alright. You know, I'm liking Gemini. ChatGPT, get out of the way. Gemini is where it's at, man. Gemini just feels... It feels more like a teacher. I don't know. It not like a teacher. It feels more like an actual website that you'd go onto, like Geeks for Geeks or something of that sort. You probably got that information off of there, but like that's probably why it's so good. But ChatGPT is a bit different. I don't know. Maybe because I don't subscribe to the Pro one. Now, once I build this baby, I'll have all the information of the internet. Well, 500 gigabytes worth. At least I'll have that much. So I'll see how it goes. Now, okay. That's that. Let me quickly check. Where was I at? I was reading the thing. I got a bit of read of this. I'm having a read of it right now. Yeah, that's pretty interesting how it works. Batch size of 2, because we're running a data set of probably 10 then, I guess in that case, or 1/5. Train loader. The rest of a training data set visiting each training example exactly once is known as training epoch. Since... Okay, how much is this one? Okay, the result is... Wait, what is this? Training dataset length, batch size 2. Okay. Training training. Training epochs. Need a random number in 1, 2, 3. Should get the exact same filling order. You know, how we figure out this a second time. So right, batch 1, batch 2, batch 3. Will change. Recorded in repeated cycles during training. So the batch order 2 here, but the third batch contains a single. Yes, because we have 5. Okay, that's good. I was like, yeah, that's why I think even numbers are better. And 5 is not evenly divisible by 2. I don't know about that. 2.5. 2.25. Is it 2.2? No, it's 2.5. Practice having someone in a smaller batch as the last batch in trading can disturb the convergence during trading. To prevent this, set drop last to choose to drop the last batch in each epoch as shown. Okay, that's interesting. So having a substantially, let's see, center shade 0, 0, 1, 0, 0, 1, 0, and then just 1. Okay. All right. That's a make. This is actually some useful information. I would have not figured this out through what's called the usual methods. Like, it's pretty good. Pretty good. This is omitted, so omit the last one. And I think this would be good in just preventing what's it called? I forgot the name. Over precision or whatever it is. Set to 0 that will be done in the main process and not separate work process in my team unplugged, but it can lead to go down so GB instead using still deep learning on GPU must also, as a result, the GPU can sit idle while waiting for GPU to trigger and multiple launch thing. However, if we are working very small data sets, numbers is one, numbers of these sensors training that only takes a fraction of a second anyway. So if we're working in tiny data sets, interactive environments such as Jupyter Notebooks, decreasing number of workers may not provide noticeable speed. Wait, what? So if you're working with tiny data sets and Jupyter Notebooks, I feel like I'm being called out here. What do you have about my Jupyter Notebook? I need the full power of it. I really do, man. When I'm working with Jupyter Notebooks, what's it called? I use it as a playground, really. I use it. It's such a fun one. I'm so happy though that Jupyter Notebooks are a thing. Instead of Java. Java. You have to compile the whole thing, you have to run the whole thing. Meanwhile, this one, yeah, I'll take that one. Everything is already in RAM anyways. Spin on multiple worker processes can take longer than initial data. Okay, third module is then gradual will the problems related to sharing resources between different it's in notebook crashes. Okay. So that can also it can cause notebook crashes. I wonder if that's something I've dealt with before. Data loading without multiple workers. So 27. By the way, if you guys want to read along with me, it is page 274 of the book. So if that's something that you guys are wondering. Data loading without multiple workers, data loading with, and a load batch is already queued up in the background. Okay. The trade-off on making holiday decision on setting the number of experiments when you can be a beneficial tool. In my experience, workers will use optimal performance, meaning real-world workers equals 4. Okay. I'll see what number of workers we can push this GPU to. If we can even do it. I did some Rock M stuff before with a comfy one. It's alright. It's alright. Luckily, we're just using a small dataset stuff. Okay, so now we are back on the main dock here. So we've read Appendix 1A.6 to load the inputs into the PyTorch data loader. Again, I love just how thorough this is. This is a really good book. This is a really good book. I love it. I should read up on my other books as well. My dad bought some books. I'll read up on that as well. But I'm just reading a book like this. So the following code uses to load inputs. No, this is the create data loader. Hold on. So this is the data set. Now creating the data loader to generate batches with the input pairs. Okay. So let's do this. Oh gosh, no. Let me copy from the thing. Create data loader. Here we go. Copy from the GitHub. By the way, if you guys are wondering where I'm copying and pasting from, if you search up for the GitHub, there is a GitHub for all of the code stuff as well. So that's really, really good. So just creating the data loader. So we created the data set class. So data set v1, we've got the actual text, tokenizer, max length with stride. What is stride index? What is stride? I don't know what that is. I've never seen that before. What is the stride inputs? Step size for the okay. That's a part of the technique that we're using. So in this code, the stride input determines step size for the sliding window as it moves across your tokenized text to create training chunks. Which controls how many tokens the window skips forward before grading the next sequence of chunks. How much will overlap with? Okay, just determines how much they'll overlap. The stride is a okay. Oh, Gemini gave me some useful info here too. Visualizing how the stride works. Max length is 3. Stride equals 1. Maximum overlap. So, just by 1 token redundant but abundant training data. 0 overlap. Just about a full length of the token. The chunks sit perfectly adjacent to each other. Why just the stride? Smaller stride. 1 of 4. Significantly more training examples out of the same source, like a form of data augmentation. The model gets a predicted. So that's pretty good. I'll do that, I think. Larger stride. Fast training and memory efficient because token belongs to exactly 1 unique input chunk. Fast training and memory efficient because every token belongs to exactly 1 unique input chunk. Let's see. Token 3, token 1. Yeah. I gotcha. Alright. There might be some contextual patterns. Okay. Although the model only sees the text broken up in one specific way, it might miss out on contextual patterns that span across the artificial boundaries of your chunks. Alright, so it can make it dumber. It can lose context, which is not good. So you want to get the smallest stride possible, really. And the largest stride is if context does not really matter. If you have a large enough data that you're working with. Otherwise, if you don't, then definitely go with number 1, even though it may be a bit slower. Okay, let's have a look at this now. So, got this. This is we've created the data loader here. So, done the thing. Create data loader. Batch size of 4. Stride of 128. Wow. Okay, that's a large stride. That's 128, but we're in like 5,000, so yeah. 100. Let me just quickly check. But full. But that's the thing. So let's see, where is stride being used here? So data set, stride. Hello, Warden. It's nice to see you, Warden. It's been a long time. Don't worry. My plan is to make it sentient, but as you can see, I'm still in the beginning of it. In terms of bricking my computer, if I did, I would be very stuffed. I would be very stuffed. But also, hello, Warden. If you want, let me know and I can send you the details of this book as well. Like if you want to code along with me or anything like that as well, because it's a really good book. I'll send you the details. I'll send you the link to it as well. I'll send you the file if you want. And that goes for anybody else as well. Let me know. So at the moment, stride is the range of 0. I guess starting from 0. Dude, I need to. I'm sorry. It's been a long time. I don't know everything about Python. Python range inputs. Function inputs. I need to. Yeah, Warden, what have you been up to, Warden? It's been a while. Been a very while. Range is 5. No, that's not it. Range, okay, 0, 1, 12. This is how range can be used to generate numbers in reverse order providing negative value. No, not that one. Oh, okay, so... Okay. So this makes sense. So, the range... So for I, for the number in the range, starting from 0 to the token ID minus the max length. So the length of the token IDs minus the max length. Number of tokenized inputs must be equal to max length. Over and then, okay, so length for token IDs minus max length. And then we're skipping it every single one by stride, which is the 128 one. So instead, it's like if stride was 2, it's 0, 2, 4, 6, 8. So that's the one there. Okay. All right. I feel good for my brain. Let's see now. Let's just download a batch size of 1 for an LLM with context size of 4, development tuition for adjective class using 2.5, and create a loader function from 2.6 together. Okay. So get this. Alright, so we've got the two tensors there. And if you guys don't know what tensors are, it's basically like a dimensional thing. So it's complex. Basically think of it as a grid. No, don't think of it as a grid actually. I don't know how to explain it. It's hard if think of it as arrays within an array basically. Like a 2 by 2 by 2 by 4 by 6 by 7, all that stuff in multiple dimensions. Alright, so executing the preceding code prints out the following, yes. And this converts the data into Python iterator to fetch the next entry via Python's built-in next function. Okay, so open encoding, so that's just normal opening, data loader, creating the data set. Batch size of 1, stride of 1, max length of 4, the data iterated. I want to see this one actually prints. Data it's hit that. So it's no, can't print it. It's okay. It's printing from memory. So yeah, it's gonna be different. So data iteratable. And then the next data iterable, right? Which, speaking of which, data iterable, let's see, that's getting it from the data loader. Data loader is create data loader v1, so it is returning data loader here. Okay, so yeah, it's returning the object, sorry, the class, well, basically the object in the class of data loader. So that's why it has all that stuff into it. Alright. First batch variable contains two tensors. The first tensor stores the input token. Yes, input token. And the second tensor stores the target IDs. Yes, so 288, all that stuff. Strings max length to 4. Each of the tensors contains 4 token IDs. Note that an input size of 4 is quite small, and choosing only for simplicity is common to train LLMs with input size of at least 256. Does that the meaning of stride? Okay, yes. So I was confused about stride one, but now we figured it out. Let's fetch another batch from this data set. Okay, but we'll do the other batch from the data set. Let's go. I went a bit ahead there. Alright, so second batch contains the following contents. If you compare the first and second batch, as you can see that second batch token ID is shifted by 1 position. For example, yeah, that's right. Which is the stride, setting the number positions and shift across badges and relating a sliding window approach as mentioned. Forget 2.14. Actually, here's one. So we can put this to max. Sorry. So batch size 1, max length 2. Stride 2. Stride is 1. Just have some fun with it. So this 2, this 2. Every single one is going to be. Yeah. All right. Okay. Now max length is 8. We have to play around with this. Boing. Let's have a look here. So every single. This is the 2. The length of the of the sensors are 8, and we go into this one. It's moving it by 2. Okay. All right. So we're 2 ahead. Okay. It's okay. Let's change this one back. Boing, boing. All right. Batch size of 1. Useful illustration. For deep learning, you may know small batch size requires less memory will lead to more noisy model updates, just like in regular deep learning. Batch size is a trade-off and a hyperparameter to experiment with when training LLMs. Okay. The heart of, stride 4. Okay, that's just the details. The stride of 4 moves the input field by 4 positions. Stride of 1 moves the yes. Okay. Let's look at how we can use data to sample with batch size greater than 1. Okay. Copy that. Paste this. And go. Boing, boing. All right. Let's see now. Data loader. Create data loader. Raw. Batch size. I can use like sample with batch size greater than 1. So at the moment, batch size of a lot. By a lot, but this is a multi-dimensional one as well. This looks to be at least maybe 3-dimensional? No, 2-dimensional. Alright, stride of 4. 3, 6. Okay. Yep. That's a little one. Don't skip a single word. This avoids any overlap between the batches, since more overlap could lead to increased overfitting. Alright, that might be an issue as well if we plan to go. I don't know. Not ChatGPT. Gemini says one thing, but this one says nothing. In terms of stride. Oh, wait, no, this is the same. Yeah, sorry, this is the same. I misread that, misunderstood that. Try to afford to utilize the set fully so we don't skip a single word and just avoid overlap. Now creating the token embeddings. So, 2.7. What page are we on? 41. I think I'm gonna take a pay. I'm gonna make some more coffee after this. So 2.7. We'll make coffee 2.8. The last step is preparing the input text for LLM training to convert token IDs, yes, into embedding vectors, which is what you see in all of the AI, what's it called? Convolutional neural networks, AI thing. You know how they have those dots and those lines? I think. Maybe I'm wrong. It's hard to visualize it. We must initialize. Okay, so firstly we've done input text. Right, we've got the text. We've done the tokenized. Token ID is done, and this is the token embeddings before the GPT decoder only transformer. So create the input token embeddings. And converting token IDs into embeddings. Here we consider previously created token ID. Script yes, okay. Wait, how long is this? 42. Okay, it is not that long. We can make coffee soon. It's 11:45 p.m. guys. I think I deserve a bit of coffee. Just a bit. Alright. So right. Here we go. These embeddings weights with random values. There's also something I don't understand fully. The whole well, I understand the weights thing. It's just different. This was the starting point for the learning process. Yes. Until we do zero shot, but zero shot's a bit different, I guess. Chapter 5 will optimize the embedding weight as part of training. To use vector representation or embedding is necessary since GPT like a deep neural network trained with backpropagation algorithm. Okay, neural networks are trained with backpropagation. Please read section B.4 in Appendix A. Okay. Let me quickly read this so that I can remind myself. Appendix A. Wait, where is it? B.4. Appendix B. Oh my gosh. Wait, where is it? Maybe A point. No. Not it. That's not it either. When the world is it? What is this again? Section B.4 in Appendix A. Appendix A. Where is section B? A. There's a lot of A's. Point 4. Oh yeah. No, it's A.4. Okay. Appendix A. Oh my gosh, this is bringing memories. This is bringing in memories. A whole lot of memories. I remember this. Oh my gosh. They lost algorithm and all that sort of stuff. This stuff, man, this gets real confusing. I remember the first time I saw this. So I always need a refresher. Every single time, I always need a refresher on this. Varied computations in PyTorch. So, any of you guys wondering if you're reading along with me, it is page 263, by the way. Yeah, it is A.4, not B.4 in Appendix A. So, rise gradient. To compute gradients. Gradients are required when training neural networks via the popular backpropagation algorithm, which can be considered an implementation of the chain rule from calculus for neural networks. Illustrated in figure 0.8. So, weight times. Oh my gosh, I'm just gonna. There's a whole lot of math stuff in here. I'm going to quickly put it in Gemini and tell me. Gemini is going to tell me what the x1 is, because I do not see an explanation for what x1 is. Gemini, where are you? What is the x subscript 1 variable in this picture represents? Explain. But besides this book is done pretty well. Even stuff that I didn't know myself. I didn't know about the TikTok and stuff. Indeed, everything changes so much, man. Technology changes so much, dude. It's amazing. Hold on. Alright, so represents the input feature multiplied by the weight. So new kilometric, okay, not that one. Reading the forward pass, yes, left to right. It's multiplied by the trainable weight, creating the intermediate value U. And calculating model's final prediction alpha and the results seeing error or loss. Okay, the gradients. During the backwards pass, to the weight and bias. Do not flow back to x1 is because x1 is constant data provided by your data loader. So you're going to change your training data to fix a mistake. You don't need to calculate a gradient update for it. Okay. Gotcha. That's really good information. Gemini, you're awesome. I like you, Gemini. I like this, man. It's like, it really is like a teacher that... So yeah, so this one times this one plus I need to in the world is this? Alright. So partial derivative of the intermediate results to Z with respect to the bias units. Okay, so that's the bias units. So the plus the bias unit is equal to Z. Alright. And then push up for that equals to alpha equals for that symbol. Partial of the derivative with respect to its inputs. What's it called? What is the U? What is that symbol? What is that? What is that O symbol? What is that O symbol? And what does it represent? Interesting. Let's see. Defining the formula. Thank you, Gemini. Oh, it's sigma. Dude, sigma has a... If you guys know math, sigma can look like the backwards E. It really is. I forgot all about the sigma, sigmoid and all that sort of stuff. Okay, so sigma that which is equal to 1 plus E to the power of negative Z, which is okay. Alright, so it's just a calculation thing. Mathematics calculation thing. Where was I at? So alpha equals that one, and then that equals a loss, and we do the back propagation. We therefore do that one, and that one, and that one. Alright. So divided by that. Okay. Alright. Call it the weights. No. I don't know. Alright, we can obtain the partial derivative of the loss with respect to the trainable weight by changing the individual partial derivative in the graph. So the loss is equal to the Okay, hold on. We can obtain wait. Sorry, guys. We can obtain the partial derivative of the loss with respect to the trainable weight by changing the individual partial derivative in the graph. Individual. What does it mean by individual partial derivative? Gemini, where are you? Where's my Gemini? What does it mean by individual partial derivative? And changing it. I'm so glad Gemini's free. The text chaining. Multi-step process. Individual part is just one single step in the graph. Okay, so we're referring. Okay, hold on. So, partial derivative of the loss. Okay, but what does it mean by partial derivative? Oh, wait, it's because it's division. Okay, what does it mean by chain of trainable weight to fix the final quality? You can't just look at one machine, you have to multiply. Yes, you have to do that. This mathematical wait, you have to multiply. Okay, so that's what the chain rule is. Fraction trick, diagonal cross. Okay, got that already. That's exactly the one you want to find. Okay. Oh, okay. So that's how it does it. Alright. So the weight of the future one is equal to essentially old. Okay. Alright. You can get the partial derivative. Or if you know the loss, you can calculate back as long as you know. If you know. The loss over weight is equal to that, so I guess as long as you know, like if you know all the details, because each and every single one that would cancel out to that. Let's see. Of the trainable derivative, but similar to both can give you the partial derivative. Okay. Hold on, it's just getting in my brain. So, try that's also something else. Partial derivative of the intermediate result Z with respect to the bias units. Okay. And if not, then you obtain the partial derivative of the loss with respect to the trainable weight by changing the eventual partial derivative in the graph. And similar to the above, okay, so it's just basic maths thingy. And similar to the above, we can compute the partial derivative of the trainable derivative by applying the chain rule. Right, so this is done. Trainable, no, that's not, wait. Okay. Why is beta the thing? Trainable derivative by applying chain rule. A bit weird. Okay, so basically, partial derivative of the loss with respect to trainable weight. So if it's in respect to trainable weight, that is where... Oh no, yeah, that's right. If it's respect to trainable weight, we have to go all the way. Okay, so by the way, guys, again, this is page 263 of the thing. But similar to the above, can be the trainable derivative of the trainable weight. Can be the partial derivative of the trainable derivative. Oh, I got it now. Okay. So the reason it's saying so, okay, this is I'm gonna just put it up on screen right now. I can do that. Let's see if I can put it up on screen. So no, that's not it. Is that it? No, that's not it. Where is it? I don't know in the world where it is. Check this out. Okay, so this is what I've been having a look with and about. So, fade out. So basically, this one is the input data, right? This is the weight. So this is something that we calculate after doing the loss stuff, just some calculations and all that sort of stuff. Of course, at first it is random. Multiply this to get u equal u plus beta is equal to z, right? And so when we want to train, and so the bias is, for example, 1 or 0.5 or 0.1, all that sort of stuff, right? So it all depends on how much trainable data is given to us. Does that really make sense? I don't know. But then again, this is 1 divided by, so sigmoid is 0, sorry, is 1 divided by 1 plus e over z, the power of z, sorry, power of zeta. So yeah, we want to trainable derivatives. This beta, the Bravo, so beta, not Bravo, beta variable b is what is trainable, because it is the bias that is allowed, basically how much of it is allowed. For example, I guess if we gave 1, the whole thing would be trainable, but if we gave 0.5, only half of it would be trainable. Okay, let's see now. Computing the loss gradient is a computational graph that involves applying the chain rule from right to left. Loss gradients, yes, from right to left. Called reverse model, automatic differentiation, or backpropagation. Okay, the most common way of computing the loss gradients in a computation graph involves applying the chain rule from right to left. But we can just sort of reverse that, right? You start from the outer layer or the loss itself. mistaking something. I feel like I've misunderstood this before. So loss is not loss gradients. So it's only a loss gradient when we do it in respect to the weight. We believe. We start from the outer layer, look backwards through the network to the input layer. We do the gradient of the loss with respect to each parameter, maintain biases in the net, which informs us how to update the parameters during training. Okay, yeah, that's likely it. Shows partial derivative, which measure the rate at which function changes with respect to one of its variables, a gradient effect containing all the partial derivatives of multivariate function. A function with more than one variable is input. We've got the root partial derivatives, circle, chain rule, don't worry. That's me. On a high level, all you need to know is this book is the chain rule. Once you can begin the loss function, given the model's parameters in a computational graph. This provides the information needed to update each parameter to manualize the loss function. It shows the process for measuring the model's performance using methods such as the gradient descent. We'll visit the computational implementation for this loop in PyTorch. That's all related to the arithmetic thing. PyTorch auto gradient, graph in the background, which called the grad function. I can impute the gradient of the loss containing the model parameter W1. The weights shown in the following. So, tensor weight. So y. Wait, which one is y again? Okay. So we have the loss. Input weight bias. Requires gradient true. Z is equal to this one plus this one, so it's this one plus B, which you can see that is correct with the order of operations. And then we take the sigmoid, and then the loss is equal to, I don't know what binary cross entropy is. F dot binary cross entropy, and then the gradients of the loss in respect to the gradient of loss in respect to the weight is this one, and the gradient of loss in respect to bias, or in this case loss to derivative, loss with respect to trainable, so trainable weight, loss with respect to the trainable weight, and compute the partial derivative of the trainable derivative. Yes, by default it destroys the computation graph after calling the gradients to free memory. However, since we use the computation graph shortly, we said retain graph equals true, so it stays in memory. Okay. The resulting value of the loss given once print. And this one, so this is the loss. Here we've been using grad function manually, which could be useful for experimentation, debugging, demonstrating, but in practice PyTorch high level tool to automate the process. We can call backwards on the loss. Gradients of all the leaf nodes in the graph, which will be stored via the tensors.grad attributes. So wait. Loss dot back. How do we? Gotcha. So loss is saved as the so that's already saved, and then we just do backward, and then get the thing. Wait. That didn't change anything. But a calculus concept, but don't worry, well, this calculus just means to explain. We need to take a PyTorch check of the calculus. We'll add a backwards method. We don't need to compute any derivatives. I remember doing this by scratch. I remember doing this by scratch in my university days. Oh boy. Back in my days, we didn't have any of this stuff. Anyways, oops, not that one. Here we go. Alright. So let me just read up on some more stuff. Where are we at right now? How long has the stream been going on for as well? The stream's been going on for an hour 30. I'm doing good for time. You know, when I actually stream, force myself to study and all that stuff, which is weird. Weird. Anyways. A bit of water first. Oh my gosh, it's so... Alrighty. Alright, so... These embeddings, random values, da 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 da. The starting point for learning process will optimize the embedding ways as part of the LM training. Yes, using the dot backwards, aka back propagation. A continuous vector representation of embedding ancestors in GPT-like the deep we've trained with the back propagation algorithm. Yes, because they update the weights every time. If unfamiliar, okay, we already did that. Today, how token embedding works with a hands-on example. Suppose we have the following input tokens: IDs 2, 3, 5, and 1. Let's put that in. Alright. For the sake of simplicity, suppose we have a small vocabulary of only 6 words instead of the 50,257 of the BBE tokenizer. Let's create embeddings of size 3. In GPT, the embedding size is 1012. Okay. Let's do that. Using vocab size and output dimensions, we can initiate an embedding layer in PyTorch, setting a random seed to 1, 2, 3 for reproducibility purposes. Gotcha. Torch neural network dot embedding. Okay, and that's already done. The print statement prints the embedding layer's underlying weight matrix. Okay. Hold on, I just realized something. How to set PyTorch to use RockM instead of CUDA. Instead of CPU. CPU. I should probably do this. Ask Google. Google, give me answer, please. Pip install torch. Done. Wait. There's another one here. Hold on. RockM will example RockM 7.2 supports. Okay, that's not something I have. Torch. No, PyTorch. Yes. Got to do that. If it crashes, rest in peace. Get started. Learn. No, this is setting it up locally. Wait. Not available on Windows still? Yes, it is. Yes, it is. Come on. Installing on Windows. Why is still not working? Well, that's not good. very not good. There must be something. Conversion of PyTorch using the command in a similar manner. Okay. Oh, we're gonna have to go to the shady places of the internet. Rock It's all PyTorch via pip. PyTorch via pip installation. Recommends current PyTorch when working for machine learning development. Good idea. I'm gonna do that. Okay, label. Gonna need the whole thing. Oh my gosh. Oh, and on the navigator. Let's clone this and then just back up. Okay. So this is not from PyTorch's original, not from the PyTorch website, but from AMD's website, which means, yeah, might be some issues. But I want to use my new GPU, and I did. I bought this as well because I know it's got AI capabilities, thanks to ROCm. So I'm gonna use it. I bought this thing. I'm gonna use all of this thing. Let's get started with Anaconda. Label loose. Give me a clone, and then we'll uninstall. Actually, we don't even need to uninstall the CUDA one. I don't think. Hopefully not. I don't think so. I'm gonna make a backup of label loose first. Call this lay blues LM lay blues LM backup. I'm gonna clone this first, and then after that I'm gonna create another one where it is going to be I've got the name, where it's going to be ROCm. Which, if you guys don't know what ROCm is, you know how basically, you know, there's ray tracing stuff on your NVIDIA GPUs, right? It's done, or DLSS basically, it's done by a thing called CUDA. And on AMD, they have a thing called ROCm for that. It's basically an AI part. Not really a, for AMD it's AI. For, what's it called? Thingy, NVIDIA, it's also AI, I guess, usually. It's just basically, for NVIDIA, it's more like computational stuff. Just specialized computational units, basically. That's what it is, specialized computational units. And, oh man, this cloning is taking a while. Gonna take a while. I just wanna do this as well though. I think it is important to make. It is always important to make a backup of your Anaconda. What's it called? Conda environments. Conda. Always breaking on me, man. Always breaking on me. It's no fun when you break on me like this, you know. Still doing its thing. Let's continue on with this. I'll fiddle around with it a bit later, I guess. Alright, so now, so back into this, it prints out the statements of the parameters, and then that also contains the graded thing. So we are creating the embedding, which is basically that thing that people like to put out in the AI. When they think of AI, it's all those nodes, which is basically what it is. The weight matrix and embedding layer contains small random values. These values optimize during LLM training as part of the LLM optimization. Moreover, consider the weight matrix is 6 rows and 3 columns. Yes, that is right. There's one more row for each 6 possible tokens of the vocabulary, and there's 1 column for each of the 3 embedding dimensions. Okay, hold on. So there is 1 row for each of the 6 possible tokens. 1 row for 6 of each program. And there's 1 column for each. Okay, so hold on. Wait. Let me get this straight. So, moreover, you can see that the weight matrix has 6 rows. Okay, so this is for the weight. Okay. 6 rows and 3 columns. There is 1 row for each of the 6 possible tokens in the vocabulary. I'm guessing this is for the next token thing. There's 1 column for each of the 3 embeddings, 3 embedding dimensions, which is of course the W1X and the what's it called now? W1X and the thingy-majiggy and B. Yes. So we're gonna print the embedding layer of tensor of size 3. Okay. There's this one. Okay, 0, 1, 2, 3, of course. So embedding layer of 0. I need to quickly get an understanding again of understanding tensors. Yeah, I need to get an understanding of the shapes and all that sort of stuff. Shape versus what's it called? It's multi-dimensional array. Yes, I already know about the multi-dimensional array bits. Okay, so 0 dimension vector matrix. Okay, so currently it's a vector. Guess this would be what? It's a torch.tensor. Okay. Wait. So hold on. Torch.tensor. Sorry, my mistake, guys. All right. It is printing the fed. Sorry, I forgot about that. This is an array, but it's just printing the third value. Okay. All right. I thought I missed something there. I suppose. Now let's apply it to a token ID to obtain the embedding vector. This token embedding vector. The returned embedding vector is this. Compare the embedding vector token ID 3 to the previous embedding matrix, which is going to be this one. This one? What are we talking about? Wait. So its corresponding next is 3. Wait. Makes this in some context here. We compare the embedding vector token ID 3. Yes. To the previous embedding matrix. Okay. talking about output dimensions, input dimensions. That's 2351. Yes, let's go to hold on. Compare the embedding vector token ID 3 to the previous embedding matrix. We can see that it's adding to the fourth row, apart from the size of the 0 index, so it's corresponding index 3. In other words, the embedding layer is essentially a lookup operation of two rows. Yeah, so the embedding layer is essentially a lookup operation of two rows from. Yes, so each individual one is an embedding layer. That's right. Personal links choose rows from the embedding layer's weight matrix via a token ID. Wait. Oh, I'm confused. Nervous perspective. Gemini, explain this to me. Explain this to me. Big takeaway here is that the embedding layer, yes, isn't doing any complex maths like multiplication and addition when it receives an input is acting as an efficient lookup table or a dictionary. Yes, okay, I know that part, that makes sense. Here's the breakdown of exactly what's happening in that passage. Token ID is the page number cannot, computers can understand raw words, so we first send into token IDs. Yes, like 290 or 49. Where is the... I don't get it. Where's that 49? Where's that from? Huh? Oh, previous code dataset. Okay. Alright, so that's the previous code dataset thing. Token IDs, yes. An embedding layer holds a giant matrix of table data that represents a unique token in the. When you pass token ID into an embedding layer, it treats the ID like a row index of page number in a dictionary. If you ask for token ID free, Python utilizes zero indexing. Yes, I know that. The layer goes straight to the fourth of its hidden matrix. That row is your embedding vector. Okay. This is a three-dimensional vector representing the meaning of token free. Yes, the meaning of token free in the vocabulary. Okay. So, vocab. So vocab is size 6. The output dimension we want is free. Of what? Okay, so the vocabulary, basically the dictionary, or the tokenizer is size 6. Size 6. And then the output dimensions of what we want to output later on is just free. We put that through into the torch.embedding. So is this just printing out the... So this is printing out the whole meaning of each and every... Oh, no, not the whole meaning. No. This is basically printing out the next word, every single next word in the embedding of what the next one could be, I think. By the looks of it. here. This is a three-dimensional vector representing the meaning of token ID 3. Yes, in a real LM, this vector is much larger than the dimensions wide. Capture deep semantic concepts, but here it is simplified to three-dimensional space. This links directly back to the componental graph. During back, okay. Okay. So, embedding layer weight. Okay. So it is. It is creating the meaning or the relationship between each. For example, this one, I guess from what my understanding is, if we really look at it, this one here is the third token, of course, ID index number 2, because 012. Third token, and its correspondence is to this one, or 0, index 0, and its relationship between token 0 and this, and it has a high relationship. That's why this one to this one, this basically this one to itself is very, very low at 0.3374. From what I'm getting at, so why are we doing this? Let's see. Token is mathematically graded and twice as much in language. So what Apple? Okay. If given raw ROM is like 3 and 4, the model will assume that token 4 is mathematically graded than as token 2, but in language, so what Apple does not. Okay, by converting this single integer 3 into the list of coordinates, give the multiple where it can position words close together if they mean similar things like king and queen, and far apart if they don't. Oh, okay. Yeah, so this is different. This is essentially grouping. This is essentially grouping. So the grouping concepts, basically precision. In zero-shot learning, everything that looks similar and similar, for example, fruits and all that sort of stuff, they're all grouped together. Flags would be all grouped together. You know, people with faces would be all grouped together. This sort of equation, we map it into a multi-dimensional plane. If they mean similar things like king and queen, yes, and far apart if they don't, yes. So it's putting the location of where it is on the map. Basically, does it make sense? Yeah. So basically, the numbers are locations on a plane. Alright, cool. I nailed it. Okay, this makes it, dude. Oh my gosh, man, you guys have no idea how much simpler this makes it, man. My understanding, my actual freaking understanding now is much better. Oh my gosh. Those numbers are nothing more than geometric coordinates. Because it turns out it's plotting in three-dimensional space, but of course it's more than 3 dimensions. Distance. Just to confirm, is the token 0. There's location, then the first twin phrase location, and the third in Python's case 4 index in the tensor array. The right was cleared up. Let's see. It makes it the 4th. Yes. No. Wait. Token ID is linked. An index 3, which makes it the 4th row in the tensor array. Look in your metrics. Count them using Python. Yes. Here is token. Yes. Okay. See. So whenever the model process, it'll reach out to physically and pull those coordinates. Okay. This. Man, it's okay. Gotcha. Okay, that's another one for the brain. Okay. All right. I need some water. This is exciting, man. Learning new stuff is exciting. Why can't jobs be like this? Some people handle monotonous jobs. Well, think of it like this. Like, if your job is meaningful, you know, your job is meaningful. I want to have a meaningful job. Maybe I should become a researcher. I'd like to do that. I like learning new things. But, yeah. We'll see how it goes. In my line of work. The Gemini has been so useful, man. You guys just don't understand how much time it saves in terms of instead of having to search stuff up. Like, dude, searching stuff up, you'll go deep and deep and deep and deep into so many things. Gemini just gives you the summary, which is very useful when you know what you're looking for exactly. And if you don't, then you can search it up and see. But yeah. Now what's the embedding layers essential look up? Yes, look up for the embedding layers weight matrix by a token ID. Alright, so and it says weight matrix. Just another word for the coordinates in the sense that you've talked about before in our chats. Yes, exactly. Embedding way. Okay, the weight matrix is the official. Okay. Alright, so the weight matrix is the official mathematical name for the entire map of coordinates. That's a good name for it. I think there's a giant atlas. The weight matrix is the whole book, and each row inside of the matrix is a specific latitude, longitude for a single word. Why it's called the weight matrix? The coordinates. Whose creator doesn't know what words mean. One small warning for the future. Okay. While a weight matrix means the map of coordinates specifically inside an embedding layer, the term weight matrix is used everywhere in deep learning. When you move past embedding layers into the rest of neural net, like linear or dense layers, okay, weight matrix changes its job. In an embedding layer, the weight matrix is the coordinate of data itself. In a standard layer, the weight matrix is a grid of multipliers. If you plot in your graph, the model takes your word coordinates and multiplies them by these weights to twist, turn, and project data into the next layer. Yes. Okay. So. Alright, I gotcha. So this is different. Different type. Basically different context of things. For the table for one hot encoding, the embedding layer approach describes it essentially just a more efficient way of doing one hot encoding. I don't know what that is. Followed by matrix multiplication. Yeah, fully connected with in a supplementary code on GitHub at because the embedding layer is just a more efficient implementation equivalent to one hot encoding with matrix multiplication approach can be seen as a neural network data that can be optimized via backpropagation. And we've seen how to convert a single token ID into a three-dimensional embedding vector. Yes, let's now apply it to 4 inputs. Okay, let's do that. Wait. Do that, and 2, 5. Wait. Wait, hold on. For input IDs. Wait, did I? 2351. Huh? Oh wait, no, gotcha. So wait. So this would be specifically for that, but now we get the whole thing. You can see number 3, 0, 1, 2. The embedding layer of the input ID 551. Gotcha. So 2, this is the embedding layer of 2, this is 3, this is 5, and this is 1's details. Gotcha. Cool. Alright, yeah, this is what I did manually for free. Okay, gotcha. And each random is multiplied, obtained via lookup operation from the embedded weight matrix as illustrated in figure 2.16. Yes, having now created embedding vectors from token ID, this will add a small modification to these embedding vectors to encode positional information about a token within a text. Encoding word position. This. We went a bit step oh my gosh, dude, me in trying to understand everything, we went a bit step forward. Gemini explained to us a bit more about this because I was like confused because I didn't know if it was going to cover it or not. I was confused what these meant. Because like if you see this, it's not gonna tell you anything unless you know what you're working with. Like these are just numbers. And you wouldn't know. You wouldn't know unless it'll just get so confusing. That's how it's always been with tensors and everything like that. So. Alright, so how long is this one? It's 2.8. Oh, 2.8 was the last one for chapter 3. You know what? I think I'm gonna finish chapter 2. And then we're gonna get chapter 3 probably tomorrow. Let's see how I go. You know, let's see how I go. Maybe we can even do more. I don't know, it's like 12:45. Do I have anything on tomorrow? Let me check. Hold on, guys. I need to do some check. I need to make sure I don't need to be anywhere tomorrow. It's not good if I gotta be somewhere tomorrow. Na, 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 na. No, it's on Wednesday. So no, by tomorrow I mean today. So today, nothing at all. Like nothing at all. All right. I am gonna grab some more coffee. And so we've done this one. And done this one. And with that, I don't know if people are following the thing. But with that, how are you guys in following it? If you are following it at home, how are you guys? Hope this is useful for you. It's useful for me because again, technology just changes so often, man. You don't. There's new methods, new stuff every single time. It's constantly learning. It's constantly learning new stuff, and I just find it lovely. I find it. I like learning new stuff like this. Like when I was doing university, we just knew about NLP, basic stuff. That was like the closest we got to that. We did do convolutional neural networks, but that was with images though, with images. So it's a bit different when it's like this. And even then, it was actually image recognition. Not even image generation, so difference. A lot to learn, but gives you the basics. But a lot to learn. Alright, I'm gonna grab some more coffee. I'll be right back. You guys stay right where you are. Maybe grab a coffee. Or two. Or three.